In the last video, we saw what the rank of linear transformation is, what the nullity of a linear transformation is, and how they are related through the dimension theorem. In the proof of the dimension theorem, we explored how the linear transformation helps in describing the relationship of vectors in W in terms of vectors in V and vice versa. So there were a couple of arguments which were inbuilt into the proof of the dimension theorem, which we would like to extract and make it into a theorem here. So let me start this lecture with a proposition which was actually covered once in the proof of the dimension theorem, but nevertheless it's a very good exercise to make it precise. So let's look at a proposition to begin with here. So yeah, so mostly this lecture will deal with how a linear transformation interacts with the basis. So let's see what is coming up. So a proposition to begin with. So let T from V to W be a linear transformation and let V1 to Vn be a spanning set of V. The proposition says that the image of V1, V2 up to Vn is a spanning set of the range of T. Then span of TV1 to TVn is equal to R of T. We had given a proof of this in the course of the argument, at least was described in the course of the proof of dimension theorem. Let's single that out. So let's give a quick proof. So what do we have to show to establish that span of TV1 to TVn is equal to R of T? We have to take an arbitrary element in R of T and show that it is in the span. So let's start with an arbitrary element. Let W be an element in R of T. What does it mean to say that an element is in a vector is in the range of T? This means that there exists a vector V in capital V such that TV is equal to W. But what do we know about V1 to Vn? V1 to Vn is a spanning set of V. So since V1 to Vn is a spanning set of V, we can write any vector of V as a linear combination of V1 to Vn. In particular, we can write V as a linear combination of, so there exist real coefficients a1, a2 up to an such that V is a1 V1 plus a2 V2 plus up to an Vn. So our vector V is a linear combination of V1 to Vn, not necessarily a unique linear combination because we don't know anything about the linear independence of V1, V2 up to Vn to begin with, but we certainly have at least one linear combination in this manner. Now consider T of V. What do we know about T? T is a linear transformation. So T of V, which is T of a1 V1 plus up to an Vn, by using an induction argument is equal to a1 times tv1. We have already discussed this once in the proof of dimension theorem. This will turn out to be equal to a1 tv1 plus a2 tv2 plus up to an tvn, which is an element of the span of tv1 to tvn. But let's be a little more careful. What is TV? TV is nothing but our W. As you can see, the choice of V was exclusively to see that, so you can see I am putting an underline here in green, the very choice of V was such that TV is equal to W. So, what we have established now is that W is in the span of TV1, TV2 up to TVN. But our choice of W was arbitrary. Hence, what we have established is that hence R of T is contained in the span of TV1 up to TVN. But TV1, TV2 up to TVN, each of these vectors are in W, and span of TV1, TV2 up to TVN is the smallest subspace that contains these vectors. This was one of the results we proved in one of the videos earlier, and therefore any vector subspace which contains these vectors should also contain the spans. In particular, this is also contained in W, in R of T. Yes, so earlier I said W, but what I meant is TV1, TV2 up to TVN are vectors in R of T. R of T is a subspace, as we know, and because span of TV1 to TVN is the smallest subspace which contains these vectors, this is contained in the subspace R of T. And this implies that R of T is equal to span of TV1 to TVN, as was to be established. So, as you can see, this was an argument which we did use in the proof of the dimension theorem, but it is worthwhile to keep a proposition exclusively to capture this. It's an important proposition. We will prove one more similar statement, and this is going to be a little different, but the style of the argument was similar or is similar to what was done in the dimension theorem. So, let T from V to W be an injective linear transformation. Suppose we start off with a linearly independent set. Suppose V1 to Vn be a linearly independent set in V. Then, as you should be guessing by now, the set conclusion is that the set TV1 to TVN is linearly independent. Let's have a quick look at the proof and you will see the similarities. So, to check that something is linearly independent, what do? We take a linear combination which is equal to the 0 vector, and we then check whether the coefficients are forced to be 0. So, let us start off with a linear combination. Let A1 TV1 plus plus AN TVN be equal to the 0 vector of W. Remember that TV1, TV2 up to TVN are vectors in W. So, this is a linear combination in W. By the properties of a linear transformation, we can write, which gives T of A1V1 plus A2V2 plus ANVN is equal to the 0 vector. Why is that the case? Because this is equal to this. The vector A1 TV1 plus up to AN TVN is equal to T of A1V1 plus up to ANVN. We just use the properties of the two properties of linear transformation to establish that they are equal, and this is equal to the 0 vector of W. But what does it mean to say that T sends a vector to the 0 vector? It means that the vector is an element of the null space of T. So this implies a1v1 plus anvn belongs to the null space of T. But in the previous video, we saw a proposition which stated, and we proved the proposition which said that T is an injective linear transformation if and only if the null space of T is the zero vector space. So this in particular is just the zero vector space. So this implies, and why is this the zero vector space? Remember that our proposition has the assumption that this is an injective linear transformation, and that's precisely what we will be using here. Null space of T is hence 0, and this implies that this vector is equal to the only vector in the null space of T, which is the 0 vector. But now let me bring your attention back to our hypothesis, which I am now again underlining in green. We have started off with the hypothesis that V1, V2 up to Vn is an independent set, linearly independent set, and therefore this forces these coefficients to be equal to 0. Ai is equal to 0 for all I, since V1 to Vn is linearly independent, and that's precisely what we had set out to prove. Remember, we started off with a linear combination of Tv1, Tv2 up to Tvn, which is equal to the 0 vector, and we have now established that all the coefficients are 0. Tv1 up to Tvn is linearly independent. All right. A combination of these two propositions gives us something quite nice. So let's prove now one more theorem. So let T from V to W be a bijective linear transformation. Then dimension of V is equal to the dimension of W. So bijective, if you recall, is a function which is both injective and surjective at the same time. So if you have a linear transformation which is both one-to-one and onto, or injective and surjective, then the dimension should necessarily be equal. So let's give a quick proof of this. It's a remarkable statement because the moment we have a bijection, we have that the dimensions are preserved. Alright, so let's start with, okay, I should have added one assumption here. So let's start off with, let V and W be finite dimensional vector spaces. So this is an assumption which I should be adding because we are not assuming that our vector spaces are finite dimensional, but this theorem we should be careful in stating it because this is a theorem for finite dimensional vector spaces. And let T from V to W be a bijective linear transformation. Alright, so since V is finite dimensional, let the dimension of V be equal to small n, and let us pick a basis. So let B equal to V1 up to Vn be a basis of V. What did the first proposition tell us? The first proposition told us that if we have a spanning set V1, V2 up to Vn, then TV1, TV2 up to Tvn is a spanning set of R of t. Now, since B is a spanning set by the proposition above, the first proposition above, which we just proved, TV1 to Tvn spans R of t. But what was the assumption on our t? T was assumed to be a bijective linear transformation. So, in particular, our T is a surjective map. It is on to W. What is the meaning of a map being surjective, a linear transformation being surjective? It means that the range of T is equal to W. So, since R of T, since T is surjective, we have R of T is equal to W. Now, R of T is equal to W means that TV1 to Tvn spans W. Okay, so we have established one aspect of TV1, TV2 up to Tvn being a basis of W. There is something else which is to be checked for it to be a basis, namely linear independence. But T is also an injective linear map, and by the second proposition, second proposition above, since T is injective and B is linearly independent, we have TV1 to Tvn is linearly independent. TV1 to Tvn is linearly independent and hence a basis. Therefore, dimension of W is equal to n, which is exactly the same as the dimension of V. So, I would like to bring your attention to another aspect in the proof of this statement. Not only have we established that the dimension of V is equal to the dimension of W, but rather we have also shown that a basis is always mapped to a basis if you have a bijective linear transformation. So, the converse of this statement is also true. So, what is the potential converse? The converse says that if we start off with a linearly independent set TV1, TV2 up to Tvn, which spans R of T, which spans W, then V1, V2 up to Vn should necessarily be a basis. So, I'll just note that as a converse. The converse is quite straightforward. Conversely, if TV1 to Tvn is a basis of W, then V1 to Vn is a basis of V. Typically, when we want to define a function from a set to another set, we have to deal with what the value of the function is at every point of the domain. So if f is from say x to y, to describe f, we will have to talk about f of x for every x in capital X. What we will now do is that in the case of linear transformation, we will see that that is not necessarily needed. In fact, that is not needed at all. We have to only specify the value of t at a basis, and that uniquely fixes what the linear transformation will be on the entire vector space. So it many times reduces our effort to bothering about what our linear transformation is on many times a finite set if the vector space is finite dimensional. So let's look at the statement to the theorem more carefully. So let me state it down as a theorem. So let V be a finite dimensional vector space and therefore it will have some dimension, say n, and let V1, okay, so let T be a linear transformation. Oh, no. I want to say that the linear transformation can be defined at a basis, and we can talk about the linear transformation being defined on V. So let me fix a basis and let V1 to Vn be a basis of V. Okay. Let W1, W2 up to Wn be a subset of capital W, another vector space. So I will not write down that. W is a, so we don't need W to be finite dimensional, that's why I didn't, okay, and W a vector space, okay. So I'll just write it in a bracket, a vector space. Okay, what is the theorem? The theorem states that then there exists a unique linear transformation from V to W such that TVI is equal to WI. Then there exists a unique linear transformation T from V to W such that TVJ is equal to WJ, or J is equal to 1 to N. Okay, let's give a proof of this theorem. So there are two things to be shown. The first being that, okay, not necessarily in that order, but we will do it in this order. First, we will show that the linear transformation is unique, if at all it exists. And then we will show that there exists at least one such linear transformation. Okay, so let's look at if S and T, let's say if S and T be two linear transformations. Of course, we don't even know whether there is even one linear transformation. We will come to that in a moment. But before that, let's look at the hypothetical situation where we take hold of two different linear transformations which map Vj to Wj. And then we will show that S and T should necessarily be the same. So let S and T be two linear transformations such that S of Vj is equal to Wj, which is equal to T of V. We will show that for every vector V in capital V, S of V is equal to T of V. So let V be an arbitrary vector in capital V. What do we know about V1, V2 up to Vn? We know that V1, V2 up to Vn is a basis of capital V. Let me just recall that part for you. It is in the hypothesis. It's a basis of, okay, so please make a correction here. Good that I came back. So this is not W. This is V. So V1, V2 up to Vn is a basis of V, right? And therefore we can write the vector V as a unique linear combination of V1, V2 up to Vn. This implies that there exist A1 to An, in fact uniquely there exists A1 to An such that V is equal to A1 V1 plus An Vn. What is going to be S of V? Then SV is nothing but S of A1 V1 plus An Vn, which is equal to A1 SV1 plus An SVn. But our assumption here, which now I am again underlining in red, tells us that for j equal to 1 to n, S of Vj is equal to Wj. Let me write here for j equal to 1 to n. And that implies that this is equal to A1 W1 plus up to An Wn. Now let us try to see what will be T of V. Similarly, T of V will also be A1 TV1 plus up to An TVn, which again by what I am by this part of this statement, this will be equal to A1 W1 plus up to An Wn, which is exactly this expression for S of V. And therefore, if at all there exists linear transformations which send Vj to Wj, then it should necessarily be a unique linear transformation. There cannot be two such linear transformations. Okay, so we have established uniqueness here. Now let us establish existence. Let's bother about existence. Well, we know what T should be on each of the basis vectors. So, given a vector V in capital V, by a theorem we have proved earlier, there exists a unique linear combination of V in terms of V1, V2 up to Vn. So, let V be a vector in capital V and A1 to An in R be such that V is equal to A1 V1 plus up to An Vn. Now we define T of V to be equal to what should be T of V. If at all it is a linear map, we know how it's going to behave on the right hand side. T of this will be exactly this. And we know that linearity forces it to be A1 TV1 plus An Tvn, and we know that Vj is being sent to Wj. So let me rub all these things and write down directly what our definition should be. Our definition should hence be A1 W1 plus up to An Wn. Now many questions will come up. First question being whether T is a well-defined map at all. Answer is yes, because of the theorem we have proved earlier, namely that if V1, V2 up to Vn is a basis of a given vector space V, then every vector has a unique linear combination of every vector has a unique expression as a linear combination of the basis vectors. So in particular, the choice of A1, A2 up to An, therefore this map is a well-defined map. Well-definedness is clear from one of the theorems before. But that's not enough, we have to check. Okay, let me just write well-definedness follows from the fact that every vector of V can be written as a unique linear combination of basis vectors. Next, however, we have to check that T is a linear transformation. So let's just quickly check that. So let V1 and V2 be vectors in capital V. We would like to check that T of V1 plus V2 is TV1 plus TV2. And let's give some expressions for this. U comma V prime works well. So let V be equal to A1 V1 plus up to AN Vn, and V prime be equal to B1 V1 plus up to Bn Vn. So we would like to check that goal. Let's just write it down as goal. We would like to establish that T of V plus V prime is equal to TV plus TV prime. Now let's look at the left hand side here. What is T of V plus V prime? Before we do that, what is V plus V prime? Let's find out what V plus V prime is. This you should check is equal to A1 plus B1 V1 plus up to AN plus Bn Vn, and therefore T of V plus V prime after all the manipulations will be A1 plus B1 times W1 plus up to AN plus Bn times Wn by the very definition of our map T. Now let's look at what is TV plus TV prime. So just to see what TV looks like, this is going to be T of A1 V1 plus A2 V2 plus up to AN Vn. Let me just quickly write it down. This is just going to be A1 W1 plus up to AN Wn. Similarly, T of V prime is B1 W1 plus up to Bn Wn, and therefore TV plus TV prime after all the manipulations, this is going to be A1 plus B1 W1 plus up to AN plus Bn Wn. I am not going to write down the which is equal to T of V plus V prime. I am not going to write down the proof for scalar multiplication, the corresponding argument, which I will leave as an exercise. Check that T of CV is equal to C times T of V for all V in capital V and C in R. So I'll leave that as an exercise. But with this, we have found out a well-defined unique linear transformation T from V to W which maps Vj to Wj, and that completes the proof. Okay, so maybe one more example is in order. So let's look at an example. From your knowledge of geometry, you will be knowing what rotation map is, right? So you take vector V and a rotation by theta in the clockwise direction will be something like this. This is what the rotation. So if this is V, this vector is what is going to be R of V, rotation around the origin, right? So you would like to define this map very rigorously. Rigorously, certainly yes, but observe that the map will certainly be a linear transformation, because if you add two vectors V1 plus V2, this is say V1, and if you add V2, V2 will be like this, the corresponding vector which gets added will also be V1 plus V2, and similarly with the dilation. So R, which is a rotation, will be, we know what it is geometrically. Let us now try to make a precise definition of the rotation map in a concrete manner. So, the theorem which we just proved tells us that we don't need to bother defining our R on every vector. If we know what it is on basis vectors, we can extend it to a definition on the entire vector space. On here in this case it is R2. So the easiest thing which we can think of where we should be able to talk about the rotation is on the x-axis, the unit vector on the x-axis and on the y-axis. So we know that the rotation of the unit vector along the x-axis is taken to, what is this? This is a, so maybe I should draw with red here. This is the vector that is being sent to, say, this is y just 2 lines. So this is say theta, and we know that this point is going to be cos theta sin theta. Basic trigonometry tells us that that is the case. So we know that the rotation maps the vector 1 comma 0 to cos theta rotation by theta, cos theta comma sin theta. And we also know what it maps 0 1 2. So okay, 1 0 was mapped to cos theta sin theta. We also know what it maps 0 1 2, 0 1 TO2. So let's see, this is say theta, sorry, this is our 0 1, it gets mapped to something like this, and this is just going to be pi by 2 plus theta, cos pi by 2 plus theta, which is minus sin theta, and sin pi by 2 plus theta, which is cos theta. So we know that 0 1 is mapped to minus of sin theta and cos theta. So our rotation on an arbitrary vector x comma y will be the following, can be defined as, by our previous theorem, r of x comma y, this is going to be x times r of 1 comma 0 plus y times r of 0 comma 1, and this is going to be x cos theta minus y sin theta comma x sin theta plus cos theta, not cos theta, it's y cos theta. And if we are to write it in terms of column vectors, x comma y is being sent to cos theta minus sin theta cos theta times the vector x comma y. So as you can see, I am somehow trying to get hold of some matrix to represent our linear transformation R, and we will very soon see that this can always be done. All right.